everyone and welcome at Phywe monthly YouTube video. Today we will talk about one of our bestseller products, namely X-ray 4.0 Expert Unit. As you might already know, studies of X-ray are included in all fields of natural science: physics, chemistry, biology, engineering and medicine. As you also might know, X-rays by its physical nature are dangerous for human beings. Therefore, to enable such experimenting, the equipment must satisfy highest safety requirements. Our X-ray Expert Unit has all necessary patents and certification according to the latest European standards. As you can see, apart from its beautiful design, it also has highly reliable lock-on door system that prevents penetration of X-ray outside of the box. Together with our X-ray Expert Unit, we offer to you the whole variety of extension sets to perform experiments in computed tomography, structural or material analysis, and way more. We also offer to you together the hard and soft copy of X-ray handbook that include detailed description of more than 50 experiments that you can perform. And now, my colleague, Dr. Anton Batalov, will present to your attention one specific experiment.
Hello everybody, welcome at this video lesson. And today I'm going to present you some special experiment using X-rays, which is the quantitative fluorescence of the alloyed materials. Okay, let's start. First, a couple of words about X-ray fluorescence. You don't see this fluorescence, but anyway, it's a process of the emission of secondary photons from atomic material. And this is a very powerful method to conduct elemental analysis of materials. Our today's exercise will be to find out the components, the chemical components of the material, which is called constantan, and which is a magic material of physicists because it keeps the same electrical conductivity independent of their outside temperature. So to conduct the experiment, we use the fourth generation X-ray versatile teaching laboratory of company Phywe, and we use it in a single photon counting regime. We employ for this a pin diode and multi-channel analyzer. The pin diode produces electrical pulses which amplitude is proportional to the incoming energy of the X-ray photons, and the multi-channel analyzer counts the histogram of the incoming photons and in this way produces the energy spectrum of the X-ray radiation. As a first step of the experiment, we have to calibrate the multi-channel analyzer. So we have to assign energies, X-ray energies, to some known lines. You can use a direct beam of the X-ray to do this, or you can use some pure materials like iron and zinc. In this case, you go to calibration of the multi-channel analyzer and you put some pure material inside the X-ray beam. So after accumulation of the spectrum of X-ray fluorescence of iron and zinc, we have a well-known K-alpha lines and K-beta lines of the discussed materials, and I can use the literature data which you can find in our software to make the corresponding calibration. I do it using 3 cursors and a 3-point calibration method, so I put just literature values of kiloelectron volts for these lines. So now the calibration is done, and the next step is go on and study the spectra of constantan and do the elemental analysis of constantan. So I put the sample inside and I use the spectral recording option of the multi-channel analyzer software. I also use the timer of the X-ray to always keep the same exposition. In this time it will be 10 minutes. So after 10 minutes, we have obtained the following spectrum of the fluorescence of constantan. So on the x-axis you see the energy in kilo electron volt, and here you see the amount of the photons with a certain energy. And the first step is a qualitative understanding of the spectrum. And with a little bit of experience you can see that it consists of two lines of copper and nickel. So this is K alpha of nickel, and this is K alpha of copper. This is K beta of copper. Okay, so now I have a plate of pure material copper inside, and I start the recording of my fluorescence spectrum. And here you see the incoming photons are being recalculated into the histogram, and you can see very clearly this is K alpha, this is K beta transition of copper. After measurement of pure materials, we are ready now to go on with the quantitative analysis of the constantan components. So here you see the results on the monitor. The blue line is the fluorescence spectrum of nickel, red is copper, and black is constantan. To find out how many percent of nickel, for example, constantan has, so you have to divide the intensity of nickel peak inside the constantan spectrum to the nickel peak in a pure nickel material. To find out the intensities of peaks better, you can use the option of our measure software of function fitting. So here you can fit, for example, normal distribution as shown here with the red line. After doing this quantitative analysis, we have obtained following values. So we have 51% of nickel and 57% of copper inside the constantan. Why these values are deviating from the manufacturer values of 55% for copper and 45% for nickel? Okay, there are several reasons. Of course, we are doing several systematic errors in this experiment, but there is also physics behind of this. So we have so-called matrix effects. Matrix effect is how the metals influence each other inside the alloy. For example, low energy photons from one metal inside the alloy can be absorbed by another metal, or it can be even increased, so the fluorescence of one metal can produce secondary fluorescence of another metal. And the real industrial machine, of course, need more perfect calibration materials to make a quality control of metal alloys, for example.
Thank you very much for your kind attention. We hope you enjoyed the topic of today. For more product information, please visit us at www.phywe.com. Shall you have further questions, please do not hesitate to contact your sales partner. Thank you very much and bye-bye.